Guys, this is Vijay and I hope you are doing well. In this video lecture, we will derive the heat conduction equation through a plane and composite wall. Let us consider a plane wall of homogeneous material through which heat is flowing only in x direction. Here you can see that this is a plane wall. There is a transfer of heat from one side of the wall to the another side of the wall. Let us consider the thickness of the wall is L. Here we are considering temperature. On one side of the wall is T1 and another side of the wall is T2. And thermal conductivity of the wall material is K we are considering. And here we are considering a small strip at distance x from the one side of the wall and its thickness is dx. So here the A is the cross section area of the wall, K is the thermal conductivity, and T1 and T2 we have already discussed temperature maintained at two faces 1 and 2 of the wall respectively. Now we will apply the general heat conduction equation, Cartesian coordinate equation for this wall. Okay, here we are considering only the heat transfer in x direction. So the remaining direction y and z, okay, we are neglecting because we are considering only one dimension. We also assume that the heat is transfer steady state, means it is not a function of time. So del T by del tau is 0. So in this equation, okay, this equation we have already derived it in our previous lecture. Okay, if you want to clear your fundamental, okay, how to derive this equation for Cartesian coordinate, for cylindrical coordinate and spherical coordinate, then you can watch these videos. So to derive the equation for plane wall and composite wall, here we are considering only one direction x. So y and z, del square t by del y square equal to del square t by del z square equal to 0, because here we are considering only heat transfer in x direction. So this first term we are considering, this second and third term is 0. We are also considering there is no any internal heat generation. Okay, there is no any internal heat generation. Okay, so with no internal heat generation, so this term it will become 0. Qg means internal heat generation by K, thermal conductivity. Okay, it will become 0. And we are considering steady state. Okay, it is not a function of time. So del T by del tau term is also 0. So the remaining term is only first term. Del square T by del x square equal to 0. But we know that there are more number of dependent parameter. At that time we are using partial differentiation, but here only one parameter. Okay, it will depend on x direction. So it is, we can also write this partial term into simple derivative term, d square t by dx square equal to 0, because there is no more dependent variable. So we are only considering first term because it is a one dimension heat transfer. So y and z is 0. Second term and third term is 0. There is no any internal heat generation, so this term is also 0. And here we are considering steady state, so this term is also 0. So remaining term is d square t by dx square equal to 0. By integrating the above differential equation twice, okay, we are getting dt by dx equal to c1. Okay, whenever we are considering the integration on both this side, so dt by dx, okay, equal to constant. Then again this dt term is on left hand side and dx term is on right hand side, means it is multiplied by with c1. And whenever we are taking the integration again on left hand side and right hand side, so dt means differentiation and integration, so it is cancelled out, so only remaining term is t, and integration of dx is x plus c2 constant, where c1 and c2 are the arbitrary constant. The values of this constant may be calculated from the known boundary condition as follows. Okay, here we are considering a boundary condition. at x equal to 0. Here you can see that, okay, x means we are considering the strip at distance x. So here you can see that from the origin, okay, x equal to 0. So at that time temperature is T1. So T equal to T1 and x equal to L. Okay, here you can see that when x equal to L, so the temperature is T2 at point 2 boundary condition. So at x equal to L, so at that time temperature T equal to T2. So this is our boundary condition. Now we will put the value one by one in this equation and we are getting the value of C1 and C2. So first of all, we will put the value x equal to 0. So at that time temperature T equal to T1 in this equation T equal to C1x plus C2. So we are getting T equal to T1 C1 x equal to 0. So this term is first term is it will become 0 because it is multiplied with C1 x C1 into 0, so 0 plus C2. So we are getting the value of C2 equal to T1. Same as we will put the value from the second boundary condition x equal to L, T equal to T2, and we are getting T2 equal to C1L plus C2. So from this equation, okay, we will put the value from C2 equal to T1 in this equation. Okay, so C2 equal to T1, and now we will make the object C1. So C1 equal to T2 minus T1 divided by L. T2 minus T1 divided by L. Okay, so this is the value of C1 and this is the value of C2. So now we will put the value of C1 and C2 in this equation T equal to C1x plus C2. Now we will put the value of T equal to T2 minus T1 by L bracket complete multiplied by x plus T1 into Fourier equation. Okay, according Fourier equation Q equal to minus TA dt by dx. Okay, it is applicable for conduction where K is the thermal conductivity, A is the surface area which is perpendicular to the heat transfer, dt by dx it is called temperature gradient. So from the previous equation we are putting the value of T equal to T2 minus T1 divided by L into x plus T1 into this equation. So here we calculate only dt by dx, then after we will put the value of dt by dx in Fourier equation. So dt by dx, here T equal to T2 minus T1 by L into x plus T1, put this value in dt by dx, value of temperature. So d by dx, okay, differentiation of this term. So here you can see that the differentiation of x is 1 and this is T1 constant term, so differentiation is 0. So we are getting dt by dx equal to T2 minus T1 divided by L. Put the value of dt by dx in Fourier equation. So Q equal to minus TA T2 minus T1 divided by L, and here you can see that this is a minus term, and whenever we rearrange the temperature, so here also minus term is there, so minus minus plus, so Q equal to K T1 minus T2 instead of T2 minus T1 divided by L. But as we know that whenever we compare, okay, with the thermal circuit and electrical circuit, okay, and current will flow due to voltage difference, and there is a electrical resistance, same as it will be flow due to temperature difference. So here only the temperature difference is there, the remaining term is in denominator. So Q equal to T1 minus T2 divided by L upon Ka. So this is thermal resistance, okay, for a plain wall. So RTH, conduction, thermal resistance to heat conduction, shows the equivalent thermal circuit for heat flow through the plain wall, okay, and its equation is L by Ka. Same as whenever there are number of layers is given, means composite wall is given. Composite wall means if the wall is made of more than one layer. Okay, here you can see that, okay, for example, in our home, okay, the bricks is, okay, overlapped with insulating material, okay, plaster is there, on the plaster surface we paint. Okay, so these are the example of composite wall. So here you can see that this is a different material. Okay, so there is a different resistance for individual layer. Okay, so there is a different resistance for individual layer of the wall surface. So here we are considering three layer. Its thermal conductivity is Ka, Kb and Kc because it is a different layer. Okay, in a composite wall of different materials. So its thermal conductivity is also different. So there is a different resistance for different layer. Okay, so we are considering for wall A, thermal resistance is RTHA. For wall B, the thermal resistance is RTHB, and for wall C, thermal resistance is RTHC. So LA upon Ka, LB upon Kb into A, and LC upon Kc into A. Here we are considering area is unit surface area. Okay, so the T1 and T4, okay, the inner and outer surface temperature of the wall, and on interface the temperature is called intermediate temperature. Okay, here the temperature is T2 and here the temperature is T4. So we have already discussed LA, LB, LC, thickness of slab ABC respectively, Ka, Kb, Kc, thermal conductivities of slab ABC respectively. Here temperature T1 and T4. Okay, this is called temperature profile because it is flow from higher to lower. Okay, so temperature T1 is higher and T4 is lowest temperature. Okay, and this is intermediate temperature at interfaces. Okay, so T2 and T3 we are considering temperature at the interface 2 and 3 respectively. Since the quantity of heat transfer per unit time through each slab per layer is same, so we know that, okay, as per the Fourier law, Q equal to minus K dt by dx. Okay, and we apply this equation to individual layer. Okay, so Q equal to minus K dt by dx, temperature difference for first wall T1 and T2. T2 means intermediate temperature, and T3 it is also intermediate temperature at interface. So for first wall A, the temperature is difference is T1 and T2. So we are considering T1 minus T2. Thickness is La, so we are considering La. Okay, same for wall B. The temperature is T2 minus T3. For wall C, or we can say third wall slab, the temperature is T3 minus T4 difference, and the thickness of the wall is LC. Assuming that there is a perfect contact between the layer and no temperature drops occur across the interface between the material. Because sometimes what's happen, there is a air gap is there, so we are also considering the resistance of this air gap. But whenever we derive this equation, at that time we assume that there is a perfect contact. Okay, so there is no any temperature drop. So from this equation we make the object temperature difference. Okay, T1 minus T2 for first term, T2 minus T3 for second term, T3 minus T4. Okay, so we are getting another equation. Whenever we make the object from these three equation, temperature make the object. So we are getting another three equation from previous equation, T1 minus T2. So Q upon La divided by Ka into A. Same for second equation, T2 minus T3 equal to Q into Lb upon Kb into A. Same for T3 minus T4 equal to Q into Lc upon Kc into A. Now adding equation 1, 2, 3 on left hand side and right hand side term. So we are getting, okay, so summation of first, second and third term on left hand side equal to right hand side. So here you can see that this minus T2, this is plus T2, this is minus T3, this is plus T3. So it is cancelled out. So remaining term is, so the remaining term is T1 minus T4. Same as on right hand side, the common term is Q in bracket L upon Ka plus L upon Lb upon Kb into A plus Lc upon Kc into A. Okay, so Q equal to, now we will make the object Q. So Q equal to, here the A is also common, here we are considering unit surface area, so it is multiplied with this term. So A into T1 minus T4 divided by this term. Okay, so Q equal to T1 minus T4 divided by the resistance of wall slab A, resistance of slab B, resistance of slab C, RTHA plus RTHB plus RTHC. If the composite wall consists of n slab per layer, then Q equal to T1 minus T plus n plus 1. Here you can see that, okay, the temperature at outer surface, okay, its number is more than 1, or we can say plus 1 as compared to the number of slab. If the slab is 4, so here T1 minus T5. If the slab is 6, so at that time T1 minus T7. So here we are considering only 3 slab, so T1 minus T4. So we can say that the temperature at outer surface is n plus 1. Okay, so if the composite wall consists of n slabs per layer, then Q equal to T1 minus Tn plus 1 upon sigma. Sigma means number of walls we are considering, number of slabs. Okay, L upon K. So this is the universal equation for composite wall heat transfer. Same as in some of the cases, for example, the wall is divided in two parts. Okay, then how can we solve the example? So in this type of cases, we are considering thermal circuit. Okay, same like as in electrical circuit, we are considering parallel and series connection. Then after, we will find out the equivalent resistance, and we will put this value in heat transfer equation, and we can solve the example. So in order to solve more complex problem involving both series and parallel thermal resistance, the electrical analogy may be used. A typical problem, its analogy, electrical circuit as shown in figure. So here you can see that, okay, for wall A, or we can say slab A, okay, it is made by same material, thermal conductivity K. So we can easily find out the resistance by equation L by K. But in second slab, here you can see that in another slab, okay, the wall is, or wall or slab is divided in two parts. Okay, the half portion of the wall, it is made by another material, and remaining half portion, it is made by another material. So its thermal resistance is different. So we have to find out the equivalent resistance for this particular slab. So here you can see that both are in parallel connection. So we will find the resistance of half slab B and remaining half slab C. And this both slab, it is in parallel connection, so its resistance is also parallel connection. So by putting the value, okay, by using the equation of series and parallel connection, okay, as we know that in electrical circuit we are using it, okay, if the resistance is series, okay, then we can find out the equivalent resistance R equal to R1 plus R2, same as if it is in parallel. So 1 upon R equal to 1 upon R1 plus 1 upon R2. Thank you friends for watching this video. I hope this content, it will be helpful to you. If you would like to watch this type of more technical videos, then please subscribe our channel and also share with your friends. Thank you friends.